Welcome back. This is the third segment of the combined section 2.4, 2.5. As you recall, we had just solved a triangle where we had, it was a right triangle where we had one of the acute angles and one leg was derived from measurement, and we solved the remaining parts and pieces of that triangle. So I'd like to kind of look at the same sort of problem and do it in a slightly different way, where we have different bits of information and we derive the rest. So I'm going to switch over here pretty quickly. And I believe we can focus. Okay, so again, section 2.4. I think I'm on page 5 now. So let's look at a different setup where I'll kind of put it over here. Again, we're still working with right triangles, so there is one right triangle. I'll keep the naming compatible with the last one. So we've got, let's, and then what labels here? So little b, little a, little c. Okay, so suppose we know, and this is kind of where we sort of started with, where we had the sides, and but we didn't really talk about how to find the angles. So let's suppose that A is equal to 44.25 centimeters, and B is equal to 55.87 centimeters. So we need to find everything else. Now, because it's a right triangle, we know that big C is 90 degrees exact. So this is kind of always stated in when you have a right triangle. It says, oh, solve this right triangle. Well, you automatically know that one of those angles is exactly 90 degrees. So we can do a calculation pretty quickly to find the third side. It happens to be the hypotenuse in this case. So C, little c is equal to square root of 44.25 centimeters squared plus 55.87 centimeters squared. Take the square root, and recall that this is, we're going to end up with some kind of bizarre looking number that will then apply rules of significant digits to. So there's 44.25 squared plus 55.87 squared equals, and then take the square root, we end up with 71.27074.715 centimeters. Okay, so that's kind of the strategy for solving for the third side. We can use the Pythagorean theorem to do so. But as you maybe as you recall, we said that you want to always use the numbers derived from that are derived in the origin of the problem, because as soon as you apply any kind of, I mean, this number, when we actually finish the process of applying significant digits, this is going to come out as 71.27 centimeters, and there's this kind of leftover change. It is critical for you to understand that when you apply these rules of significant digits, you only apply them at the end. If we had to use little c for some further calculation, we would not use the rounded value. We would use this thing, and as many of these digits as we could hold, because you end up with something called a rounding error, which needs to be avoided. And I can show you numerous examples as we go on where a rounding error will cause you all kinds of problems. These sorts of problems are not terribly complicated at this point, but we do get into some stuff that's a little more. So basically, here's what I want you to think of. If you're going to apply significant digits, only do it at the end. For our purposes, if we needed to use the number c for a calculation, like, you know, maybe there's a sine or cosine in there, this is the number we use. And so to avoid this sort of weird business at the end, we'd like to just use a and b whenever possible. Okay, so to move on here, the next sort of calculation that we're going to try to do is to find angle A. Well, note that the tangent of angle A is equal to the opposite over adjacent, which is A over B, which tells us that since A is an acute angle, that A will be equal to the inverse tangent of A over B, which is something that we did in the previous section. So plugging in the values, that's the inverse tangent of, well, A is 44.25 and B is 55.87, which will give us 44.25 divided by 55.87. Take the inverse tangent, gives us 38. Now, there's a debate. Sometimes these problems ask you to do these in degrees, minutes, seconds. So I'm going to go ahead and just convert that to degrees, minutes, seconds. And there it is. We got, now I run out of digits on this, on my screen, because this particular calculator will only give me out a total of 7 digits, but this is 38 degrees, 22 minutes, 47.3 seconds. That's as good as I can pull off my calculator. And I'll apply significant digits here in a minute. The other angle, tangent of B, is just the reciprocal, B over A. Sorry, tangent of B is B over A, which implies that angle B is equal to the inverse tangent of, just kind of flip them upside down, B over A, which is equal to inverse tangent of 55.87 divided by 44.25, and 55.87 divided by 44.25. Then take the inverse tangent. And again, I'm going to do it with degrees, minutes, seconds. So going to degrees, minutes, seconds, there's my value, 51, 37, 12.6. So 51, 37, 12.6. And notice these don't actually add up to 90 degrees. And that's because of this rounding business. They should be pretty darn close though. And it should be out here in this last digit. All right, so to finish out the problem then, I'd want to write down all the known angles. So I've got A. A is 38, 22, 47.3. Now, it should have, because the inputs are 4 and 4, it should have a total of 4 significant digits. Now, be careful. There's a tendency to forget that this is closer to 23 than it is to 22. Right, because you're so used to rounding at 5. So this is actually 3823, which has four digits of significance. B, notice that that's 5137. That gets rounded down, so 5137. And then, of course, C is 90 degrees exactly, given in the problem. A was given in the problem 44.25 centimeters. B was given in the problem as 55.87 centimeters. And then C, which we calculated right here, 71.27, blah, 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 blah. Notice it's a result of a Pythagorean calculation where both of the inputs have 4 digits of significance. So the result should have 4 digits of significance, so 71.27. All right, so there's kind of the final solution to this problem. And I think there's some examples in the homework. I'm not going to beat you up with these too much because I think that this is a pretty straightforward concept. Once you start using the right trig functions, a lot of times what I see people do is not actually write this first bit, and they sometimes get confused. It's A over B, or B over C, or whatever. It's worth it to write it down. To actually write the algebra instead of just going to bang and then an answer, because sometimes this is wrong. It's just, for whatever reason, it has been my experience over the years that students, when they're doing math homework, don't actually want to write all their work. It's like, what if you make a mistake? How would you know where the mistake is? It's very hard to find it. It's a good practice to get into. Just write everything down. Okay, so let's move on to some more complicated examples of actual, and this we're almost getting into something that's a little practical. So section 2.4, now I think we're on page 6. Okay, so let's imagine that, how are we going to apply this? What are we going to do? So often in different types of surveys, be they tree surveys or land surveys or things like that, there's a lot of trigonometry that's used. And so I'm going to try to use an example of one that I know. When you're performing what's called an ALTA survey, which is American Land Title Authority survey for extended insurance on a commercial property, often you are asked to determine the height of a building above the ground. So to kind of stylize that, this is sort of the setup of the problem. You've got sort of a building that has some height, call it H, total, and there's some sort of terrain. It's unlikely that you'll be exactly at the, wherever the bottom is. So H is the number that we're wanting to compute, right? We want to be able to determine the value of H. Now, you could walk up to the top of the building and you can drop a tape measure down and you can measure it. That's usually very impractical, and especially if this is a building that doesn't have a stable surface or a good way to approach the edge, like, for example, the top of a steeple or something like that. But anyway, so as a simplistic version of this, if you can imagine, you're standing out here, right? And you have a direct horizontal line of sight to the building, and you had a device of some kind, which are, there's many of them out there. You'd probably be using, depending on how accurate you want it to be, maybe it'd be a more or less precise instrument. But if you had a way of measuring sort of this angle of ascent and this angle of descent, and you knew the distance away from the building, and there's ways to do that as well, optically, or you could pace it over. I mean, whatever. There's many different ways to do that. So let's say that we know this distance, the horizontal distance, and we know this angle, which we're going to call alpha, and we know this angle, which we're going to call beta. Okay, so to calculate the height, we actually need to solve two triangles. I mean, it's the easiest way to do it, right? That's a right angle. And so we've got sort of the upper triangle and the lower triangle. Let's call this sort of leg of this upper triangle A, corresponds with alpha, and B. So we're going to do a little bit of math here. So note H is equal to A plus B. And if we look at the tangent of alpha, note that's going to be the opposite over adjacent. So tangent of alpha, alpha is a positive acute angle, that's A over D. And similarly, if we look at beta, again, positive acute angle, it just happens to be angled downwards, but it should be B over D. So tangent of beta equal to B over D. So if I rearrange these, I've got A is equal to D times the tangent of alpha, and B is equal to D times the tangent of beta. So to find H, it's just A plus B. We'll use the expressions on the right. So H, and I'll actually factor. So H is equal to D times the quantity tangent of alpha plus tangent of beta. And if we had measurements, right? So the measurements that would be made is the distance, the angle of ascent, and the angle of descent. We would plug them in and we generate the height. I don't think that it's, we could probably try one. So let's say that D is equal to 143.2 feet. And let's say alpha is equal to, let's say it's 11.14 degrees, and then let's say beta is equal to 28.28, or sorry, 28.22. Okay, everything's got 4 digits of significance, so I'm not going to get too worried. The result is going to have, strangely enough, is 4 digits of significance, even though it shouldn't be that way. But let me show you why that happens. And again, it's a good rationale for why significant digits does not make sense. Okay, so h then is equal to this d, so 143.2 times tangent of 11.14 plus tangent of 28.22, right? And when I calculate this, I get 11.14, take the tangent, plus 28.22, take the tangent. Now multiply this number by 143.2, and I end up with 105.04609337, etc. So let's go back to the problem and say, well, how many digits of significance should I use? So this number would have 4, and this number would have 4 digits of significance. Even if I add them, they're going to be in the same position. You'll find that that's true. And this number out here has 4. So I've got something that's 4 times 4. So the result should have 4 digits of significance, right? So I know that this is very, very close to the round off, and for whatever reason, and I've said this before, people want to round this to 105.05 or something, or I don't even know, 105.046. But we have to round it at this position, the 4th digit of significance, 1, 2, 3, 4, and unfortunately, fortunately or unfortunately, we're going to get 105.0 feet as the final result. Based on the rules for digits of significance. So relatively, I mean, we're starting to get a little bit more complicated geometry, but it all just comes down to like measuring things based on right triangles. So this is kind of I think maybe this is one of the more complicated examples in section 2.4. And there is one additional example that I want to cover from 2.5 because there's a couple of interesting problems that result, and it is actually somewhat practical. There is a way to use this, and I have actually done it before. I've done this before too. I've made these kinds of measurements, but not exactly the way that I've described them, but using these sorts of inputs to generate these values. So I think this particular segment's probably getting a little long. So I will finish here, and then I will probably have one more segment to finish off the one example I want to do from 2.5. So I will see you again very